Okay, we're gonna get started. So obviously we got into organic chemistry last time, and we were specifically talking about alkanes. And alkanes, again, a reminder, sort of the functional group, if you want to call it that, really, is really carbon-carbon single bonds, and that's what makes something an alkane, is the presence of just single bonds, no other type of bond, no double bonds, triple bonds, or anything like that for it to be an alkane. As we talked about, the alkanes are really important, especially the first 10 alkanes for our purposes here, because pretty much everything is based off of those names. So, as we mentioned last time, sort of the quicker you get those names and the formulas that go with it, the much easier everything else will be. Alkanes have a general formula of CnH2n plus 2, and the N there is the number of carbons. So CH4, which is one carbon, would be 2 times 1 is 2 plus 2 is 4, is methane. C2H6 is ethane. C3H8 is propane. C4H10 is butane. C5H12 is pentane. C6H14 is hexane. C7H16 is heptane. C8H18 is going to be octane. C9H20 is nonane. And lastly, of the first 10 there, C10H22 is decane. So again, pretty much everything will come down to those 10, and for our purposes, they are all alkanes, and as you can see, they all end in ane, just like the sort of group name, if you will, and that is how they all basically will end. Remember that there's a few different types of formulas that we also saw. We could have just the molecular formula like our C3H8. We could also have the condensed formula, which would be something like CH3, CH2, CH3, where we do not draw out the hydrogens. We also could have the expanded structural formula, where we do draw out the hydrogens, kind of very similar to like a Lewis structure. So molecular formula, condensed, expanded, and also we talked about line structure, which is just lines there, and really nothing else attached, nothing else really put there unless it is some other element than carbon. And once again, not usually drawn like these dots, but everywhere there's a dot here, which is where a line ends, or two lines that come together will basically be carbons. And remember, the other thing that we talked about is carbon pretty much wants to have 4 bonds. So it will continue to make bonds until it has 4, typically in organic chemistry. And in carbon in general, you usually don't find too often lone pairs or dots on carbon. So it typically will make bonds with lines, and it will only need 4. And our other important rule with organic chemistry still applies, which is hydrogen. That should only have basically 1 bond. Hydrogen should never be in the middle. Hydrogen should never have dots around it or anything like that. It should just have basically 1 line. So the same sort of Lewis structure rules we talked about in terms of carbon and hydrogen still obviously apply here with organic chemistry as well. And this guy at the end is sometimes referred to as line structure. We got into a couple things there at the end, which was the idea of isomers and also how to name alkanes. And when we have isomers, those are basically the same molecular formula, but different connectivity. So I think we might have looked at pentane, I think, which is something like this. And that is, again, just 5 carbons straight across there, which would be pentane. We could, again, maybe not do 5 carbons across, but maybe something like this. Do better than I did last time. Let's see here. No. This might have been one of the ones we drew, I think. So again, they both have 3, 6, 9, 10, 12 hydrogens. They both have 4 carbons. Remember that one of the best ways to determine whether or not you sort of drew an isomer is to name both structures. And if they do end up with different names, then they are isomers of each other. Again, if they end up with the same name, they're really the same guy, just maybe drawn differently. So really the first rule of naming pretty much any organic compound, as we talked about, is we're always going to be looking for the longest carbon chain. And remember that it does not always has to be the straightest, but the only rule is when you're counting sort of carbons is you can't backtrack. So you got to kind of go in one direction until you hit a dead end. And that's just how many carbons you have. You can't, again, go one way, back up, and go the other way. So it's got to be one continuous swing from one direction to the next. Once you do, it will probably match one of those 10 alkanes, and that'll be sort of the base of your name. Anything else that's sort of attached to it that is not part of the longest carbon chain are what are sometimes referred to as groups or substituents. And there's a couple of different types of groups. There's alkyl groups and there's halogens or halo groups there. And alkyl groups is a fancy word for basically carbon groups. And they are also based off of those first 10 names. The only difference is, as we talked about, is they will have one less hydrogen that's going to allow them to basically attach. Because something, for example, like methane that has 4 hydrogens to that carbon has no more room to attach to another carbon because it will have too many bonds. So these alkyl groups will have one less hydrogen. Where that one less hydrogen is where it's able to bond in. So again, if we looked at something like our methane, which is this guy here, it is pretty much filled up. But if we take one hydrogen off, for example, the guy on the left there, this now becomes a methyl YL, just like the alkyl here group. And it has that extra space where that hydrogen was to attach in and still not have too many bonds. So once you have your longest carbon chain, really the next thing you want to do is identify what groups you have going on. Once you do that, you want to number the longest carbon chain. And the way that you want to number is whichever way gives the groups, in this case, the smaller number. So when we're talking about naming alkanes specifically, it is actually the groups that have the sort of priority, if you will, as to which way you want to number it. And it is whichever way will give those groups the smallest number. Once you have your longest chain, once you've identified all your groups that are there and you numbered it the appropriate way, what's left is to actually name the thing that's left over at that point. And we do name based on groups first, and again in alphabetical order. And that is alphabetical order, again, regardless of any type of prefix that may be there, and also alphabetical order regardless of the numbering. So sometimes people think, again, as we might have did an example last time, like, well, that guy's got like the smaller number, but it's not alphabetically first, so I should go with that one because of the numbering. and it doesn't really matter the numbering. It doesn't matter if there's a prefix. When I talk about a prefix, you can use prefixes like di for 2, tri for 3, tetra for 4, if there are multiples of the same group attached. And it doesn't have to be to the same carbon, but just in the same compound. For example, you have, say, 2 methyls, like I think we might have looked at an example last time. You would insert dimethyl in front of the name. And again, they don't have to be on the same carbon. They can be, but they don't necessarily have to be just 2 or more. They're in the same compound. Once you do that based on the groups, then the base of the name comes at the end. A couple considerations. We always do between a number and a letter, a dash, and that's also a letter to a number, whichever way you're doing it. And if we have 2 numbers, which can occur, we do use a comma in between the 2 numbers if you happen to have 2 numbers back to back in a row. So if we were looking at this one here that I drew, we would want to look for the longest continuous carbon chain. And once again, we could go 1, 2, 3, and then up for 4. So that would be 4. We could also do, if we wanted to, I suppose, 1, 2, 3, and 4. That would also be 4. I think no matter which way you go here, you're going to get 4 in a row, which is going to be the longest continuous carbon chain. My recommendation again is if you got one that's kind of straightish, maybe go with that. And again, the carbon there at the end on the right is part of the longest continuous carbon chain. Again, because we can go up and we could go over, we could go back down. The only thing we cannot do when we're counting is backwards. Yeah, so you can't backtrack anywhere along the way. So because the longest carbon chain here is 4, that means, again, the basis of this name that we looked at is going to be butane, I hope. So the basis of this name will be butane, which is based off of the 4 carbons. Here we do have a group attached in this case because it's not part of the longest continuous carbon chain. And that is a 1 carbon group, which again is based off of the first 10 alkanes. So 1 carbon is methane, but because it's a group, it's now a methyl group. So again, those names cross over everywhere. So this is a methyl group. And now, as we talked about, there's really 2 ways that you can number this chain. You could go left to right in this case, 1, 2, 3, and 4. If you're going to number the carbons, you could also number right to left, I guess, or starting at the top and coming down, 1, 2, 3, and 4. In this case, we are going to give the priority to the groups that are there. And because of that, we want the smallest numbering. And that means in this case, left to right is going to give that group the smallest number at carbon number 2. By the way, once you lock in your numbering, everything else needs to be numbered according to that way. You can't keep switching which way you're numbering. So once you decide based on the groups that are there, which way you want to number the carbons, everybody else gets numbered according to that. So once you kind of lock that in, wherever everybody is at that point, that is the numbering you should use for them. So here we won't use the bottom numbering, and we see that that's at number 2. That means this would be 2-methyl butane in this case. Again, 2-methyl butane. The naming part of it is really all about location. As I mentioned last time, you're pretty much telling everybody where you can find everything. So when we look at a name like that, that means butane. That tells the person you got 4 in a row. And at the second carbon, you should find a methyl group hanging out there. And that's basically, you know, how the name comes about. Any questions on that? Yeah. After the alphabetical order, you do the base name. Yeah. I guess I should put name on that. Thank you. Other questions? Now, again, we also talked about drawing it from the name, which, as I mentioned, I think is kind of the easiest of all, because it kind of tells you what you need to draw. But the rule when you draw, you always want to start backwards on the name. So let's just say we wanted to draw this guy from the name. Here we would start in this direction. And because the back part of the name gives us really the number of carbons in the longest continuous chain, that's really where you should start in terms of your drawing. So if we were to sort of work our way backwards on this guy here and just clean up a little room, that's exactly where I would start. And as I mentioned before, if you're going to draw it, you should really just start with the carbons. Don't worry about the hydrogens at this point. So butane would mean we have 4 in a row. And in this case, I'm drawing my 4 straight in a row. It doesn't matter if I drew them straight in a row or move them up or whatever it may be. In this case, that takes care of really the base of the name. And because you're drawing it, you do have the option of numbering either left to right or right to left. And again, once you decide whichever way you're going to sort of number it, you got to stick with that numbering for everything that's attached. So here, again, I'm going to go left to right, which means that would be, say, my carbon number 1. That means right next door would be carbon number 2 in my case. And that, based on the name, is where I should find my methyl group. And as you can see, I have completely crossed out pretty much the name at this point. And when you get to that part, pretty much nothing else is left other than hydrogen. And the goal here, as we talked about, is to get carbon to 4 bonds. So to know how many hydrogens you should add, you just want to see how many lines are coming into that hydrogen. So the guy on the right here has 1 line coming in, which means to get to 4 bonds, he needs 3 hydrogens to do that. The guy next door to it has 2 lines coming in, right? 1 on each side, which means he needs 2 hydrogens there to get the 4. Guy next to it actually has 3 lines, 2 on the side, 1 coming down, right? Which means it only needs 1 hydrogen to get the 4. And the guy at the end has only 1 line coming in, which means it would also need 3. And now you have, obviously, what I just drew there would be the condensed formula, right? If you wanted the expanded formula, you would just draw the same thing with the hydrogens all drawn out. If you wanted the line structure, remember it makes the zigzag sort of shape because of the tetrahedral geometry there is. And that would be 4 carbons happening there. And you can still do the same thing. I'm going to go left to right on mine. So the guy at the very, very end, I'll put a dot. You don't usually put the dot, but once again, that little dot there would be carbon number 1 for me. That means right next door at the peak would be carbon number 2. And I'm going to do a methyl group. And because this is line structure, that would be a methyl group right there. A line with nothing at the end. Because a line with nothing at the end is a carbon that should have 3 hydrogens, right? Because it has only 1 line coming to it. So in line structure, as we talked about, is sort of a basic bare bones sort of structure. Not very much is added unless it's something other than hydrogen and carbon. So for example, if I did draw something like this, at the end of that line is a chlorine, which means that's a chlorine, not a carbon. So if there's nothing drawn at the end of a line and line structure, it is going to be probably a methyl group. But if they do want something at the end of that line, they will put it in there, like the chlorine in that case. By the way, that name for this guy then would be, it would be 2-chloral butane in this case. We still have the base of 4 carbons, right, which is butane. And if we number here 1, 2, 3, and 4, that's going to give us the smallest number for the chlorine. If we went the other way, that chlorine would end up at carbon 3, just like it kind of, the methyl would have ended up there. And this would be 2-chloral butane in this case. Remember, the halogens are sort of named like that. So fluorine is fluoral, chlorine is chloral, bromine is bromal, iodine is iodo. So those are the way the halogens are sort of named. Question on any of that stuff there? All right. Fun with structures. Here we go. All right. So why don't you give this one a name while we're here? Okay, so let's take a look. So I think longest carbon chain here is going to be just straight across there. That looks like 5. The only other option would be go straight across and then down, but that only gets you 4, no matter which way you do that. So that's obviously less than 5. So straight across here is going to be our longest carbon chain of 5. So really the base of our name is going to be pentane, as that is 5 carbons. Here we have actually 2 groups hanging out. We got us a group right about there. And we got one right about there as well. So we got these 2 groups, which we can identify and sort of name. As we just talked about a second ago, our Cl will be called a chloral group. Down here, we have a 1 carbon group, which is based off of methane. So that's going to be a methyl group. Now what's left again is our numbering. So if we went left to right here, that's going to be carbon 1, 2, 3, 4, and 5. So going left to right, that's going to give us a group at carbon 2 and a group at carbon 3. If we went right to left here in terms of our numbering, we got a 1, a 2, a 3, a 4, and a 5. So going right to left, that gives us groups of 3, numbering of 3 and 4. So we should go which way? We should go the top way. Again, it is, as I mentioned before, as simple as 2 is smaller than 3. So that is all we're looking for. So we're going to essentially lock into place here the top way of numbering, as that's going to give us our groups on the smaller number. So we now know that our chloral group there is going to be at carbon number 2, and this methyl group here would be at carbon number 3 in this case. That's all we need, I think. We want to go here alphabetical order. So C for chloral before M. So this would be 2-chloral dash, again, between the letter and the number, 3-methyl. Can maybe join it up there. Not bad. All right, so that is going to be 2-chloral, 3-methyl pentane. And again, as I mentioned, it really is nothing more than just location where everything's at. Pentane tells you got 5 carbons in a row. And at carbon 2, you should find a chlorine. And at carbon 3, in this case, you should find a methyl group. Any questions on that there? Yeah. Something we also talked about last time was cycloalkanes. And cycloalkanes are really alkanes where kind of the ends come together and they make sort of a ring type structure. One of the deals with cycloalkanes, as we talked about, is it has a general form of CnH2 times N. It actually has 2 less hydrogens than the straight chain, because in order for those other carbons to come together to kind of lock it into a ring, you do have to sacrifice basically 2 hydrogens, 1 on each of the carbons. And that happens in organic chemistry as you add bonds. Every time you add like a double bond or a triple bond, as we talked about last time, you pretty much need to sacrifice a couple of hydrogens, 1 on each of the carbons within those bonds. Otherwise, people will have too much. These ones, I would say, are typically drawn as line structures, and these are almost like the geometrical sort of shapes that you see, a lot like your triangle, which is our cyclopropane, your square, which is your cyclobutane, your 5-member ring here, which is cyclopentane, your 6-member ring here, which is cyclohexane. They are also still based off of the first 10 alkanes. We just add cyclo in there. So one of the things that we talked about was if it only has 1 group attached to that sort of cycloalkane, you actually do not need to give the number. You just name the group like we see in this example here. Obviously, the entire cycloalkane is the longest carbon chain, and that's going to be our cyclohexane, as we see in the name, as it has 6 carbons. Again, 1, 2, 3, 4, 5, and 6. We have a 2-member group hanging out there, which is based off of ethane. And because it's a carbon group, we make YL at the end there. So it's a ethyl group. And because that is the only group attached to that guy, it's always assumed no matter where it's at, it will be carbon number 1. So we don't really need the number. And that's why we just call it ethyl cyclohexane. It would be, if we drew this, this one would also be, if I get out of the way, this one will also be ethyl cyclohexane. It's just the same guy, just turned, basically. And this guy would still be carbon number 1, just like this guy would still be carbon number 1, basically. So if there's just one group attached, you don't need to give the numbers, just the name of the group. But if you do have multiple things attached to a cycloalkane, then you do need to give some numbering. And as we talked about, I think we did an example at the end there last time. If you have an option as to no matter which way you go, it's kind of the same numbering, you would want to give the lower number to the alphabetical guy. In some cases, that's maybe not possible, but you would want to maybe give it to the lower number to that alphabetically first sort of guy. Any questions on that there? All right, so obviously we went through naming these guys here. All right, so why don't you draw 3-bromo, 1 chloral butane. Why don't you also draw both the condensed structure and the line structure for that? Why don't you draw something? Let's do 2, 3. Diethyl for bromo, no, for iodo. We'll do heptane. All right, give that one a go. I'm gonna hope for the best as I'm just making it up clearly as I'm writing it. So, all right, just clean that up a little bit. All right, so 2,3-diethyl 4-iodoheptane, both condensed and line, and 3-bromo 1-chlorobutane, both condensed and line. Backwards, so we'll start with this one working backwards. So the base of the name is butane, which means that should be 4 carbons. And once again, I'm just going to start with the carbons. That pretty much takes care of that. Now, again, you can number left to right or right to left. For me, I'm going to go that one as carbon number 1 again. If you want, you can do it on the other way, the other side. So with that being said, at carbon number 1 here, there's a chloral group, which means there should be a chlorine hanging out there. So that is done. And since I called this carbon number 1, for me, carbon number 3 would be this guy right here, where there is a bromine hanging out. And in this case, as you can see, we went with B over C in terms of the naming, regardless of the numbers, larger on the B versus the C in terms of the name. At that point, there's nothing left but hydrogen. So the one on the far right here has 1 line coming in, which means it needs 3 hydrogens to get to 4. Guy next to it has 3 lines, which means it just needs 1 hydrogen to get to 4. Guy next to it has 2 lines, which means it needs 2 hydrogens to get to 4 bonds. And the guy at the end actually has 2 lines, which means it needs 2 hydrogens there to get to 4. That would be obviously our condensed structure. It doesn't matter if you drew the chlorine or the bromine below or above like I did. It's both basically the same. You can even draw it at the end and the guy at the left there. Any questions on that one there? Our line structure, you really could do the same thing. You could start with 4 carbons in a line structure, just like so. And that would take care of the butane part. You want to figure out which one's your number 1. So I'm going to start with this guy as carbon number 1 for me again. And that means actually on that one, I do need a line to a chlorine. That gives me my chlorine connection there. And then at carbon number 3, which would be right about here coming down, would be where my bromine would be. So here we do need to write the Cl and the Br, because if we just draw lines, it means methyl, which is not what we want to draw in this case. Yeah. Any questions on that one there? All right, coming up to this guy here on the right, we got heptane, which is 7 pack in a row there. So 1, 2, 3, 4, 5, 6, and 7, I think. 3, 6, and 7. So that's going to take care of the heptane. I am again going to start with this one on the left as number 1, which means at carbon number 4, I have an iodine, which is what 4-iodo means, right? It's iodine. At carbon number 2, which would be here, I have a not a methyl, I actually have an ethyl group, which should be a 2-carbon group, something like that. And at carbon number 3, since it's getting a little crowded up there on top, I'm going to go below and go with another 2-carbon group. And that is why we have di, right? Because there's 2 of these ethyl groups in this compound. They don't have to be on the same carbon, but they can, but we do not need them to be. Now we're ready to just fill in some hydrogens. So guy at the end needs 3. This guy needs 2. This one needs 2. This one needs 1. This one also needs 1. That one needs 1. And this one needs 3 in this case. Any questions on that one there? Once again, our line structure, same deal. We're just going to do 7 to start with. So that's 2, 3, 4, 5, 6, and 7, I hope. 1, 2, 3, 4, 5, 6, and 7. Once again, I'm going to go left to right. So that's going to be my carbon number 1, just like it's been. So that means at carbon number 4, 1, 2, 3, and 4, I will have my iodine hanging out. At carbon number 2 here, I think, we will have an ethyl group, which you could draw again, 1 carbon, 2 carbons, right? And at carbon number 3, you could do kind of the same deal if you like, without the circles, but there's the 2 carbons as well. Any questions on that? You could, I would say, typically speaking, in line structure, if it's anything that's a carbon and really a hydrogen, it's usually represented by the lines rather than that. I would probably be okay with it, but in normal cases, you would probably not kind of mix those 2 together type of thing. So, other questions? Now, as you can see here, obviously it's okay with anything that's other than carbon, like the iodine or the bromine. Other questions? Okay. All right, so let's name these 2 here, and why don't you also give the name of this that I'm going to draw, I think. Pretty straightforward. 1, 2, 3, 4, and 5 going to be our longest carbon chain in this case. That's going to give us a base name here of pentane. In this case, we have just 1 group hanging off, which would be a chlorine, and that would be a chloral group. You can probably see it, that numbering right to left here will give that chloral group the smaller number. Obviously, if you go the other way, you're going to get a larger number. So that's like a 2-chloral, and then that's all we need, I think. So 2-chloral pentane in this case. Any questions on that name there? Looking at the next one here, I think also straight will work. 1, 2, 3, 4, and 5. If we did any other sort of a movement, 1, 2, 3, 4, if we went up, 1, 2, 3, 4, and 5 if we went down. So it looks like 5 no matter which way you go. As we might have talked about last time, and just a reminder that there are instances where you can get obviously the same number of carbons going in different directions, and it really doesn't matter which one you pick in terms of the longest carbon chain. You should end up with probably the same name regardless, but sometimes just the straighter one's a little bit easier to kind of see everything. So we'll do that. So this also is going to be pentane. Here we have a line and a line, and as we've been talking about, that means that each of these are methyl groups. And once again, here we actually have 2 methyl groups in this compound, which means we have the dimethyl happening. We do need to get the locations, so going left to right, 1, 2, 3, 4, and 5. Going right to left, 1, 2, 3, 4, and 5. And it does appear here going in this direction will give us these smaller numbers, as we have a group at carbon 2 and a group at carbon 3, versus going in the opposite direction. Those groups would end up at carbon 3 and carbon 4, which is obviously larger numbers. So it's always smallest when we're naming an organic. So we'll get rid of that numbering there. So we do, in this case, need to give both numbers. So this would be a 2, 3, as we're going numbers back to back there, dash dimethyl, because there's 2 methyl groups in the entire compound, and finishing it up with pentane in this case. Any questions on that name there? Okay, so looking at our cycloalkane. Our cycloalkane would be our longest carbon chain. And apparently I drew the right one. It goes with the slide. That's also pentane, which is 5. So that's going to be cyclopentane in this case. Once again, we do add cyclo in front of it as it's a ring structure. Here we have 2 groups hanging off. We got a methyl group. We have a chloral group. And we do need to give some numbering. So in this case, there's two things you want to think about when you go to number. First off, there is a difference depending on sort of which way you go. And what I mean by that is if you start here and you go clockwise, that's 1, 2, 3, and 4, right? And that would be groups at 1 and 4. If we go sort of counterclockwise, that would be 1, 2, and 3, 4, 5. So actually, in this case, we would want to go counterclockwise, right? Because that's going to give the groups actually a smaller number. So that's one consideration that you want to think about. The second consideration is where you should start number 1 there. Should it be at the chlorine or should it be at the methyl? And in this case, if you don't erase part of the structure, put that back maybe. There we go. In this case, we would actually probably want to start numbering at the chlorine because alphabetically that's going to come first. You would get the same numbers, by the way, right? If you did start here and went this way, 1, 2, and 3, obviously you have 1 and 3 happening. But again, we would be putting kind of the lower number on the methyl, which since we have the option of doing it the other way, then that's probably the better way of doing it. So we would want a number sort of starting with chlorine there and coming to the methyl, and that would be 1, 2, and 3. You could continue numbering if you wanted to. So that'll be a 1 chloral, 3 methyl, and now we're ready to put it together here. We're going to get a 1 chloral, 3 methyl. I'll try to squeeze it in. 3 methyl cyclopentane. Yeah. Any questions on any of those names or drawings or any of those things? You clearly need to be able to do both. Give the name if you have the structure, or draw the structure if you have the name. Any questions? Okay, So let's talk a little bit about some properties of alkanes. As we talked about earlier, alkanes are really saturated hydrocarbons. And again, saturated means that they have the maximum number of hydrogens that they should. A lot of alkanes, as I might have talked about earlier, are nonpolar. And because of that, they are held together by very weak dispersion forces, which means that, you just look at them wrong and they're going to go into the gas phase. And a lot of like organic guys are actually gases at room temperature, like we see methane, ethane, propane, and butane. Alkanes have 5 to 8 carbons, are also volatile liquids. So volatile means kind of what I just said. They will hop into the gas phase very, very easily. So as we mentioned last time, that's usually why they throw you in a fume hood when you're working with a lot of these organic guys, because just very easily they can kind of go into the gas phase. And a lot of organic guys are very flammable as well, so they don't want any like Bunsen burners near them usually. So pentane, hexane, heptane, octane. Octane's pretty expensive, especially when you want to fill up your car, right? And by the way, how they get those things, they just crack big long chains of carbons into smaller ones and then charge you $6 a gallon for it as we go there. 9 to 17 carbons are liquids with higher boiling points and are found in motor oil, mineral oil, and all kinds of fuel. Lots of alkanes with lots of carbons like 18 are solids like waxes at room temperature. And the more carbons you get, the more nonpolar it gets as well. We also see, by the way, an increase in the boiling point, for example, of alkanes as the number of carbons increase. And that's because alkanes will typically use, again, dispersion forces. And dispersion forces is a way one sort of nonpolar molecule can interact with another nonpolar molecule. And basically what happens is essentially nonpolar molecules, if you remember, basically are sharing electrons equally. So they're like neutral. They have no like positive side or negative side to the molecule. But what can happen is the electrons can kind of go one way or the other, and they can temporarily become a molecule that has a charge, which if they're still next to this other nonpolar guy will make that guy temporarily gain a charge. And now for a very short period of time, they're able to sort of interact with each other. But it's very weak because it's dependent on something happening, like the electrons going one way or the other, or some polar molecule coming by for a second to kind of mess up their electron clouds. So these will eventually kind of break apart and reform new ones. And that's different than, again, something like water, for example, which is a polar molecule. And water is more negative on the oxygen, more positive there on the hydrogen side. And because it's polar, it actually has a fixed charge always. It's always positive on the hydrogen. It's always negative on the oxygen, which means when it tries to interact with things, it's good to go. It doesn't have to wait for something to occur. And nonpolar guys like alkanes, they kind of has to wait for something to occur for them to be able to properly interact with one another. So what that relates to in terms of the size of it and boiling point is very small alkanes have less electrons, so there's less opportunity for those things to kind of move around, and they have very low boiling points. But even with dispersion forces, as you put on more carbons and stuff, every time you put on more carbons, there's more electrons. And more electrons means there's greater opportunity for those electrons to move around. So there's actually better interaction between larger nonpolar molecules and larger ones. And that's why you see the boiling point when you have something like an alkane start to increase as the size increases, because the dispersion force actually gets stronger with more electrons and more molar mass. So even though it's a super weak sort of interaction, it actually can get stronger as there's more electrons, and more electrons comes with more atoms and more in that molecule and stuff like that. So that's why it says here 9 to 17 carbons actually have much higher boiling point than, say, those earlier ones, because they have a lot more electrons. There's a greater opportunity for those dispersion forces and more areas where they can interact to happen, and will keep it together much stronger. Higher boiling point is a result of things wanting to stay together, right? And what happens at the boiling point is something goes from the liquid phase to the gas phase, right? So the stronger the attractive force between, say, a molecule and another one, the harder it is to break them apart to get them into the gas phase at the boiling point, and that is a result of it being a higher boiling point. Something like methane, where it's not held together very strong at all, doesn't take a lot of energy to get it to the boiling point, and it has very low boiling points and melting points and things of that nature. Any questions on that there? In terms of solubility and density, alkanes are pretty much nonpolar because they pretty much contain carbons and hydrogens, which are nonpolar. That makes them insoluble in water, and that's because, again, water, as I just mentioned, is polar. And what water wants to do is a intermolecular force known as hydrogen bonding. And that is a bond between a hydrogen and an oxygen, nitrogen, or fluorine. It's a really strong intermolecular force, and it is the force that water uses with itself. So when it wants to interact with somebody else, it's looking for somebody else that can also do that, like hydrogen bonding thing. And when you get an alkane that has no chance of hydrogen bonding, and a reminder that even though an alkane, for example, has a ton of hydrogens, those are all nonpolar bonds, which means none of those hydrogens can hydrogen bond. So don't be fooled by the name of hydrogen bonding, that all you need is a hydrogen. You need a hydrogen that is directly connected or bonded to either nitrogen, oxygen, or fluorine. And if you look on the periodic table, nitrogen, oxygen, and fluorine is upper right, which is the most electronegative elements you could have. And that means when either of those elements hook up with hydrogen, you're going to get a pretty good separation of charge, a nice polar bond, where one side is going to be more positive and one side is going to be more negative. And that's why it's able to hydrogen bond, because you have a pretty good separation. You might even remember, for example, the bond between hydrogen and fluorine, when we did the difference in electronegativity, it was like 1.9, and 2 is like ionic almost, right? So that's a pretty big separation of charge if you have a bond between hydrogen and fluorine, or hydrogen and oxygen, hydrogen and nitrogen. That's going to create a side to that bond that's more positive and a side that's more negative, and that's going to work well with water, for example. But alkanes don't have those bonds. They have just nonpolar bonds, which basically are neutral bonds, so they have no way to interact. All molecules interact pretty much the same way. They all pretty much interact between positive and negative. So the negative side of one molecule is attracted to the positive side of the other, and vice versa. That's pretty much how every single molecule, the same molecules reacting, different molecules trying to come together, that's essentially how they interact with one another, is through positive and negative attraction. And in this case, our nonpolar alkanes have no positive or negative side, really. They have no way to maintain that interaction with water, which has a positive side and negative side, which is why they're insoluble in water. They're also less dense than water. They're typically, if you put them together, they won't mix. They'll have different layers, and usually the organic layers up on top, the inorganic layer or aqueous layer or water layers on the bottom. Any questions on that there? So alkanes do go through a couple reactions, one of which we talked about, and that is the combustion reaction. And in a typical organic reaction, we have an organic molecule like our methane. O2 is present, and it will make CO2 and water. Is pretty much your classic, bless you, organic combustion reaction. That's pretty much what happens when you light your Bunsen burner and the gas comes out of the valve right there. A little spark, you get some heat, and you get fire that occurs in that case. Another type of reaction that alkanes actually undergo are what are referred to as substitution reactions. And in a substitution reaction, there's substitution reactions and there's addition reactions. In a substitution reaction, much like the name implies, something comes off, somebody comes on. So they substitute for each other. So when you have an alkane like this guy here, for example, and we add it to like a halogen, like say Br2, for example, maybe a little light or energy used to do that. What's going to happen is one of these hydrogens in a mono-substituted situation, every single hydrogen that I am circling, they're all the same. They're all what are referred to as equivalent hydrogens. It doesn't really matter. So what's going to happen in this case is I cannot just throw a bromine on there, right? Because there would be too many bonds. So what happens is one of the hydrogens go off. And in this case, one of the bromines go on in its place. So that's the substitution part. Hydrogen off, bromine or chlorine, if you do it with chlorine, comes on. And one of the first rules you should learn when you draw what happens at the end of a reaction in an organic process is not much changes. People always want to draw all kinds of weird things, like there's got to be really things moving around. Not much changes. The only thing that changes is I took the hydrogen off at the end. I should throw the bromine on at the end. Everything else is exactly the same. Nothing else changes. By the way, a hydrogen came off and I have a Br. That's an H plus and a Br. They will come together and make HBr. Yeah, so that's the hydrogen that comes off as H plus. And the Br is Br minus will come together to make HBr. This is what's referred to as a substitution reaction. This is what's referred to as a mono-substituted product. In most cases, that is what you want to draw, mono meaning one. So just take off one hydrogen and put on one of the halogens. So if you take an alkane with a halogen, Br2, Cl2, whatever it may be, you basically pop off a hydrogen, put the halogen in its place. Everything else stays exactly the same. Don't change it. And you'll have the right product when it's all said and done. Doesn't matter if it's a cycloalkane, by the way. This is basically Cl2. Although they are not drawn here, each of these carbons has a couple of hydrogens, right, coming off. So same thing would happen. Hydrogen goes off. One of the chlorines go on in its place. And you will end up with a Cl attached there at the end. And you will also end up with HCl when the hydrogen and the other chlorine come together to make what's left. So these are two types of reactions that alkanes undergo: combustion reaction and also what is referred to as a substitution reaction. And different than an addition reaction, which we'll talk about, substitution, somebody goes off to make room for somebody coming in. So that's kind of the deal. They kind of switch places. Any questions on alkanes? Okay, let us continue on here. So we're sort of going to be transitioning here from talking about alkanes to the next couple of organic groups, which are kind of based again off of the alkanes. I think we got the combustion there. We're going to go into our alkenes and alkynes, which are the next couple of sort of organic groups. And once again, as we talked about, each of these organic groups that we will go through, which I think will be all of them, they all have what is referred to again as sort of a functional group. And that functional group is the part of the molecule that makes it that specific type of organic compound. So the carbon-carbon single bond, as we dealt with alkanes, is sort of like the functional group for it. When we get to alkenes, that is the carbon-carbon double bond is the functional group for it. It needs to have a double bond happening. And when we get to alkynes, it is the carbon-carbon triple bond. And these are the functional groups for each of these. The good news, as I mentioned before, is they're pretty much still based off of the first 10 alkanes. We will do some slightly different things because they have a double bond and a triple bond. So here is ethine, which is commonly called acetylene, and it has a triple bond. Once again, this would be our functional group that's happening here, which would make this guy an alkyne. And as you can see, this guy ends in YNE. So there's that name right there, ends in YNE. It matches the sort of group name, if you will, of the functional group. So let's take a look at each of these here. So alkenes and alkynes. Alkenes and alkynes are guys that are referred to as being unsaturated. And they are unsaturated because they have at least a double bond or a triple bond. And if you remember, as we were just talking about, saturation means that that particular carbon has the maximum number of hydrogens that it could have to get it to 4 bonds. But as we also talked about, there is a consequence for every time that you put on another bond, like when you have a double bond or a triple bond, you're going to have to sacrifice some hydrogens to do that, so you don't have too many bonds that occur. So for example, if we look at our guy here, which is all single bonded, and we saw earlier, that is ethane. And that has a formula CnH2n plus 2. But now if I wanted to double up the carbon there, I cannot just draw a line between those two carbons because each carbon will then have like 5 bonds, right? Which is too many. Remember, still the octet rules in play here. We can only have 8 electrons, 4 bonds. So in order to add a bond to those carbons, I have to actually get rid of a hydrogen on each of those carbons. And when I do that, I can now make my double bond and still have only now 2 hydrogens on each of those, as I need to lose again 1 hydrogen on each of the carbons to do that. That now has a double bond, which makes it not an alkane like we have here. It makes it now an alkene, ENE. And this guy actually has a general formula of CnH2 times N. And we are missing that plus 2 because we lost 2 hydrogens to make the triple double bond in this case. So if we look at this one, 2 is N, 2 times 2 is 4. It actually only has 4 hydrogens, again, because it has that extra bond that is there. The good news is when we go to name this, it is still based off of 2 carbons, which is ethane. But because it has a double bond, it becomes what is known as ethene, E-N-E, just like alkene ends in E-N-E. So still based off of our alkane, has 2 carbons, now becomes the alkene and becomes ethene would be its name in that case. Any questions on that? This is a unsaturated situation because in a saturated situation, if you had 2 carbons, you should have 6 hydrogens. But because of that double bond, we only have 4. And that's what it means to be unsaturated here, because we had to get rid of those 2 to make the double bond. Now, if I wanted to triple bond this guy up here, once again, I cannot just draw a 3rd line. Otherwise, each of the carbons would have too many bonds. So we have to, as we go from our double bond to our triple bond, once again, we need to sacrifice 2 hydrogens, 1 on each carbon. And now I have room where I can make my triple bond. And I am down to only 2 hydrogens in this case. This is now an alkyne, YNE. Carbon-carbon triple bond happening. It has a general formula of CnH2n minus 2. So alkanes are plus 2. This guy, because you have to put that triple bond on, is minus 2. So in this case, 2 times 2 is 4. Minus 2 is 2 hydrogens, which is what we're left with here in this picture. So our single bonded is ethane based off of our alkane. Our double bonded is ethene based off of alkene. And this guy is ethyne, YNE, based off of our alkyne here, which is YNE. Again, all based off of the alkane name. You can see just a slight difference in how we name it because of the double bond or the triple bond that is present. Any questions on that there? All right, so this is unsaturated hydrocarbons where we lose them. By the way, we'll talk about it in just a bit here, but if we wanted to put the bonds back on, we took off hydrogen to make the bonds. We would have to put hydrogen back on to break the bonds, right? It's basically going the opposite way in this particular case. So identifying alkenes, they need to contain at least one double bond. And now because they have a double bond, the bond angle actually changes from what we see in the tetrahedral geometry of our alkanes. In this case, if you remember from geometry, we have one electron pair, two electron pairs, and double bond counts as only one. So this has 3 electron pairs and also has 3 bonds. So this carbon, 3 electron pairs, 3 bonds. It makes our trigonal planar geometry, which is our triangle geometry, basically. So this makes our trigonal planar geometry, which is our bond angle of 120 degrees. So unlike the tetrahedral geometry of 109.5 that we see, which really gives our zigzag sort of shape, here we actually are moving to a more trigonal planar geometry because of that double bond that's in play. So some people may draw the line structure slightly different if there's a double bond, but for us, I think it's okay. You would just add a double bond going on there, basically, and that's how you would do it, perhaps there in line structure. So ethene is C2H4 with our double bond in the middle. Alkynes, as we talked about, will have at least one triple bond. And again, that triple bond is necessary. We have to lose a couple of more hydrogens. And when we look at this example that we just looked at where we have a triple bond, and we look at the geometry of this carbon right here, we have 1 electron pair, and once again, triple bond counts as only 1 as well. So technically speaking, that carbon has 2 electron pairs and 2 bonds. Geometry of that is actually linear. So as you put on another bond here to make a triple bond, the geometry will actually become linear, and that's 180 degrees. And sometimes you'll see people when they draw line structures actually just linear out the drawing there and make it more like a straight line. You could do that. I'm also okay if you still want to kind of have your base zigzag thing happening and just add your triple bond, something like that. That's okay as well. But sometimes you will see books and stuff straight in and out because technically speaking, the geometry there is going to become linear like a straight line. So you'll kind of see that triple bond drawn in sort of a straight line sort of fashion, especially when they're doing line structure. But like I said before, if you still want to kind of zigzag in, not straighten out, you don't necessarily have to do it straight. You could just add the triple bond like we did there. Question on that there. So let's talk a little bit about how we go about naming these guys. And I'll do it right here, I think. So when we have a double bond or a triple bond, and we need to name an alkene or an alkyne, we still do pretty much the same steps. We're going to look for the longest carbon chain. But it's really important when you do this time that it does has to contain the double bond or triple bond. So you can't avoid it. So you got to find the longest carbon chain that has the double bond or triple bond in it. that is going to give you the basis of your name, or the base of the name. It's going to be based off of our 10 alkanes, but you do need to do the adjustment of either adding ENE if it's a double bond, or you need to adjust it and add YNE if it's a triple bond. So we're still going to kind of fall back to those first 10 alkanes, but you do need to do the adjustment there to either ENE if it's a double bond, or YNE at the end if it is a triple bond. But this sort of first part of the name will still be based off of how many carbons there is. Now, different as well is this. You will then maybe not so different yet. You will still find your groups that are attached, just like normal. Now, what is different is you do need to number the longest carbon chain. And what takes the priority is the double bond or triple bond. So what I mean by that is, before, when we were naming alkanes, the way that we would number it, right, was whichever way gave the groups the smaller number, right? Here you want to number whichever way gives the double bond or the triple bond the smaller number. So it is the double bond or triple bond that takes the priority here. So you want to go whichever way gives the double bond or triple bond the priority, the smaller number. So that is your sort of defining factor as to which way you want to go, is where the double bond or triple bond is sort of located, and whichever way gives that first carbon in the double bond or triple bond the smaller number. Once you've done that, all the other groups will be named like normal or numbered like normal. The second thing that's different actually comes up here. And when you go to name the base part of your name, if there is, frankly, I would say 3 or more carbons, well, maybe like 3 or more carbons, probably 4 really. You do need to give the number of where the double bond or triple bond is located. So in addition to changing the last part of the alkane name to ENE or YNE, you also need to give the location of where the double bond is located when there makes a difference, where it could be more than one place. And that's probably more realistically, probably about 4 carbons in is where that probably would make a difference at that point. So probably more realistically about 4 or more carbons. You got to kind of do that. So what do I mean by that? Let me draw some things here and we'll see how we can kind of do this. Let's just say we got maybe all right, let's take a look at this guy here. All right, so we want to find the longest carbon chain in this case. And in this case, the longest carbon chain looks like it is straight across. And we do need to make sure that the double bond in this case is part of it, which it is in this case. And that is 1, 2, 3, 4, and 5 carbons. So the name of this would be based off of 5, which is pentane. But because there is a double bond, we get rid of the pentane and it now becomes pentene, ENE, because there's a double bond. We have a chlorine that is here, which is a chloral group. And now we need to number this chain. So we can number it 1, 2, 3, 4, 5. Or we can number it 1, 2, 3, 4, and 5. Should I go left to right or right to left in this case? That is both answers, I think. Yes. So one of those should be right. So yes, one of those is right. So in this case, we do have a double bond, right? And we also have a group hanging out there. Between the two, in this case, which one takes priority? It is the double bond. So we want to go whichever way gives the double bond in this case, which is different than what we do with alkanes because there is no double bond or triple bond. There's just groups. So in the alkane case, we look at the groups as being most important. But here, now that we have a double bond or a triple bond, that is what's most important here. And in that case, we would want to number left to right in this case. And so I'll get rid of the bottom numbering there, as that's going to be the correct way to go. And once we, just like before, sort of lock in our numbering as having to go this way, that means the group has to be locked into that numbering as well. And that would put our chlorine at carbon number 4 in this case. And again, you can't do two numbering, one for each thing. So you have to lock in the numbering one way and keep it for everything that's there. Now, the additional thing that we need to do is, because this is like 4 or more carbons, that double bond could be in different locations. So we need to tell people where that location is. And that double bond starts at carbon number 1. So this is not just pentene. This is 1 pentene. 1 is the location of the double bond, and that is what that 1 represents. So that 1 represents this guy right here, the location of the double bond. And again, you have to give that sort of number when you're not naming these type of compounds, because let's just say I drew this guy. I zoomed in, and then I zoomed out, and then I lost everything. All right, there it is. It's back. All right, so let's just say I drew this. And we got a chlorine there, and 3 there, 1 there, 1 there, and 1 there, and 3 there. In this case, the longest carbon chain is still 1, 2, 3, 4, 5, right? So this is still going to be pentane. And now that we see the double bond that's in there, it's going to go from pentane to pentene. We are going to number 1, 2, 3, 4, and 5, as if we go the other way, 1, 2, 3, 4, and 5. Going left to right still gives our double bond the smaller number, right? So we would still want a number in this direction. That still gives our chlorine a number of 4, but more importantly at this point, though, our double bond in this case is at what carbon? It is at 2 and not 1, and they're both pentene, right? So you need to tell people, no, in this case, my double bond's at carbon number 2 rather than carbon number 1, because it could be in multiple places. So that's what I meant there at the bottom when I said, if it's 4 or more carbons, usually what that will mean is there is a possibility that that double bond could be at different locations. And because of that, you need to tell people, hey, it's at carbon 1 in this case, it's at carbon 2 in this case, or whatever it may be as you kind of go through it. Everybody see the difference there and why we need that number. And again, the 2 there is the location in this case of where the double bond is for that particular guy. All right, so now that we got the double bond location, all that's left here is to name our group, which is our 4 chloral. So putting it together, we would go same thing, alphabetical, regardless of prefix. So just like we did with alkanes, we would go 4 chloral And this would be 1-pentene. The guy up here on top would be 4-chloral 2-pentene, right? So that would be 4-chloral 2-pentene versus 4-chloral 1-pentene. So both double bonds and triple bonds gain the priority in terms of numbering. You also need to insert into the name, in addition to changing the last part to ENE or YNE, you have to give the location of the double bond if there is more than one possible place that that double bond can end up. Any questions on that there? All right, then why don't you name these guys? And why don't you also draw, let's do 3-methyl to butene. Why don't you also draw 2-ethyl 4-chloral 1-hexyne. And tell you the truth, I just went for it. We'll hope for the best there, yeah. All right, so let's do names on the left there. Hopefully some pictures there on the right. Hopefully it'll work. There's a 50-50 chance. It's good. It's not bad. They pay you $1 million in baseball if you hit the ball 50 times out of 100. In fact, they would pay you $1 million if you could hit it 30 times out of 100 and have a 300. I did, because I feel like it's not going to work out right. Feel like I'll have too many bonds if I left it like that, right? Well, I'm almost 50% now. Like, hopefully the first one works, and then it'll be 50%. That'll be good. By the way, if you drew the first one, you should have had too many bonds happening there at carbon number 2, probably. Yeah, how we did. We'll start with the ones that should work, which are on the left here. So we're gonna go longest carbon chain. That's 1 there, 2, 3, 4, 5, 6, 7, and 8. And I don't see any other way to go than that. So that's 8, which would be based off of octane, but we do see hopefully a double bond happening there, which would then make it octene. Do I need to get a location of that double bond? I do, because there's definitely more than 4 carbons happening there. So we do need a number, and in this case here, we need a number one way or the other, and I'll get rid of my dots here. So we will number perhaps left to right goes 1, 2, 3, 4, 5, 6, 7, and 8. Which looks much better than if I went right to left, which would be 1, 2, 3, 4, and 5. And I'm just going to stop there because that's where my double bond is, right? Which would be at 5, as opposed to going the other direction where my double bond would be 3, right? And that's obviously the way we'd want to go. So we'll get rid of what's on the bottom there. So we would want to go numbering in this direction, which would give our double bond again where it starts there at carbon number 3. And that would be a 3-octene, and that would be it, I think, in that case. Any questions on that one there? All right, coming to this one. Looks scary. We should skip it. No, we won't. All right. So we got a carbon here, by the way. Yes, that's 1. Next carbon is right there. 2. No, I could be wrong. It's my first day. It's all right. But there is a carbon there, by the way, because otherwise that triple bond would keep going, I would imagine, right, to the next spot, and it doesn't. So They didn't get lazy halfway through the triple bond and go, that just feels too big. That's actually where the other carbon is. And then perhaps there's one here, which would be 3. That would be 4. That would be 5. That would be 6. That would be 7. And that would be 8. Kind of happens because they linear it out, right, in a straight line as the geometry there. So it should be carbons on either end of where that triple bond ends. I lost track. That's 2, 4, 6, 8. Who do we appreciate there? So that's 8. The other option would be 1, 2, 3, 4, 5, 6, and 7, which seems less than 8, so that's not so good. We could perhaps number from the other direction. So if we numbered from the other direction there, 1, 2, 3, 4, 5, 6, 7, and 8. Why should I not choose that 8? What's not in it? The triple bond. So once again, when you number the longest carbon chain, if there's a double bond or triple bond, it's got to be part of it. Yeah, so you can't avoid it. So even though we got 8, it would not be the correct 8 because then we would name this as an alkane, right? Rather than an alkene, since this has a double bond. So that's what it means by it has to include the double bond or triple bond when you're numbering the longest carbon chain. So we would not want to go in that red direction. So I think that leaves us the original blue direction there with perhaps that second carbon if we still want to believe it's there or not. So we'll go with that. So that's 1, 2, 3, 4, 5, 6, 7, 8. So that's going to be octyne, YNE, yes, as it's a triple bond happening. Here, we do want to number that chain, and I'm imagining you could see that going left to right is going to accomplish that for us. And that's going to be obviously our smallest number that we're going to have. So that's a 1 octyne in this case. That means that we have a group hanging off right about here. And that group has how many carbons? It does have 3. 1, 2, and 3. We don't count this carbon because that's part of the main chain, right? So it is only 3 in this case. 3 carbons is based off of propane, but because it's an alkyl group, that now becomes a propyl group. Yeah, YL. This is a normal propyl group, not the isopropyl that we saw the other day as well. That's a CH3, CH3. And that is at carbon number 4. Now I think I'm out of stuff to write there. So that's going to be 4 propyl, 1 octyne. Yeah. Any questions on that naming there? Yeah. So again, with the triple bond, you got to be careful both sides. And especially if it's drawn like that, it makes it kind of hard to see it. So otherwise, again, the triple bond would extend to that carbon 3 if that was the next carbon that would be there. Any questions on that there? Okay, so we got to draw some here. So we got 3-methyl-2-butene. Okay, 3-methyl-2-butene. All right, so we'll start with the butene. So butene is based off of butane, which is 4 carbons. So that seems like a good place to start. 2 means that the double bond, right? Because it's ENE is located at carbon number 2. So just like the other one, you could go left to right or right to left. I'm going to call this carbon 1 for me, which means right there should be my double bond at carbon number 2. That takes care of that. Because this is carbon number 2, that means right next door is carbon number 3, which should have a methyl group. And now everything else should be hydrogens, which will look something like this. Guy with a double bond there has 4 bonds already, right? So no hydrogens on that second to last carbon. That is the condensed structure I just drew right there. If we wanted to do line structure, we could do the same thing. We'll start with our 4 carbons. I'll call this guy once again carbon number 1. And that means at carbon number 2, I should have me a double bond happening like that. And at carbon number 3, I should have a methyl group, something like that. Yeah, so it looks something in that ballpark without the little arrow there to begin with. Any questions on that one there? All right, so now the one I switched up there at the last moment. What did I end up with there? 3-ethyl 4-chloral. So 3-ethyl 4-chloral 1. What did I do? Hexine, right? Yeah. Maybe help me. Yeah. All right. All right. So hexine is hexane. So that's 6 carbons. 1, 2, 3, 4, 5, and 6. I hope. YNE means it's a triple bond, and 1 means I laid it up right there at carbon number 1, hoping to avoid what I didn't avoid, but oh well. So that is there. That means at carbon number 4, which would be, if this is 1 for me, number 4 would be right about there. We have a chlorine. And the reason I moved it off of 2 is if I put a bond at 2, how many bonds does that guy now have? 5 too many. Yeah, it happens, when you're making up things, I suppose. So much better, perhaps, if I moved it over there to carbon number 3, where I got a little bit of room to work with. So that's going to be a 2-carbon group. And now we're just going to fill in some hydrogens at this point. We need 3 there. We need 2 there. We need 1 there. We actually need 1 there. We need none there. And we need 1 there. Yeah. Any questions on that one? Once again, line structure here, we would start with the 6 carbons, 1, 2, 3, 4, 5, and 6, I think. 1, 2, 3, 4, 5, and 6. Triple bonding, I'm just going to do it right up front there. So that would be my carbon 1, obviously, to the left of that triple bond. Carbon 2, in my case, would be the point, since I didn't flatten it out, so it's easier to see in that case. So that's 2, that's 3, and then 4 would have my chlorine. And at carbon number 3 would have my ethyl group. So something like that there in a line structure-ish type fashion. Yes. Any questions on drawing, naming alkenes or alkynes? Yes. Oh, yeah. Yeah. Okay. Okay. No worries. Yeah. Yep. Other questions? Okay. We will lay it up there.